Speaker is Anais Moller from Swinburne University, and she's going to be talking to us about the French broker system, Fink. So Anais, please take it away whenever you like.
Perfect. Thank you very much, Gautam. Um, Good morning, everybody. Here in Australia, where I am, it's actually the morning. I'm sorry I'm not there with you to talk about Fink and share a little bit more about explosive transients, but today I'm going to tell you about supernova science with Rubin and Fink. This, of course, is behalf of the Fink collaboration, and I am as well presenting some of the results of the dark energy survey that I think it's a good precedent for what we can find in LSST. So we all know that Rubin will provide us with so many detections every night of time domain objects, whether they are variable or transients, that we have a unique opportunity to discover and characterize the transient sky. In particular, and these numbers are subject to change, we're talking about millions or thousands of supernova there just to understand their astrophysics, their environments, use them for cosmology, etc. So I think one of the biggest challenges, and I'm sure you have heard about this in the last couple of days quite a lot, is that we want to identify supernova, of course. We want to identify it as early as we can for triggering follow-up and also connecting with other telescopes and data to have multi-wavelength, multi-messenger analysis, like exciting objects like kilonova, but also triggering follow-up when it's needed, whether it's spectroscopic, photometric, etc. Now, to deal with this challenge, we have created Fink. It's designed for Rubin, so it's actually quite scalable for the big data that we will have with Rubin. And we are one of the brokers selected by the project to become a community broker. So basically, we will be receiving the data in real time for the next 10 years when it starts LSST. And as Gautam say, it's supported by the French CNRS, and it's going to be deployed in the Supercomputing Center in Lyon. However, Fink is more than just French. We are a community, about 30 researchers in 7 countries and counting, including this side of the world in Australia. Now, the idea in a nutshell of what we want to do is to take this huge amount of data, enrich it, select the different types of transients and variables that you're interested in, and distribute it to maximize science. And this includes coming from these 10 million and doing filter streams that you can customize for your science case. So right now we have a series of them, but we want to grow even more. So a little bit what we have been doing aside for preparing for Rubin, well, we signed an MOU with CTF. And since February 2020, we are processing the live alert stream from CTF, which is around 1 million detections per night. However, in our database, because we pull this manually, we have alerts since mid-November 2019, but before that, we don't have any of that data. The data is already available in the finkportal.org. You can take a look and see some of the events that I'm going to show you today and new events. So the first thing that we do when we get CTF data and when we get Rubin data is we do a species of cut, which is not really a cut. We select things that are not bogus or artifacts like bad pixels or pixels. This is about 30% of the stream. We keep the data, however, but it's not displayed if the first detection was a bogus, just simply because we don't want to start detecting bogus events that have one detection every night, so many. Then I'm going to tell you a little bit how we go through the process of enriching the data in Fink. So we enrich it in different ways. One of the ways is cross-matching with catalogs, for example, in coordinates, to see if this object is already a catalog variable star, for example, or to know some contextual information, is it close to a galaxy? So right now we have implemented SIMBAT, KIDR3, a couple of variable star catalogs, and of course, MPC. But another way of enriching is we're cross-matching with footprints, whether it's through a VOE event or a GCN notices or something that you have tailored already. I want to get this footprint and try to find any alert that is within this area. With all this information, we also do, on all these alerts, keep the enriching. So we are not making any cut here. So we also get other types of information, like features like rates and colors of the light curve, but we also do a lot of machine learning. So we have a series of machine learning scores, classifiers, that will classify all light curves, and we will provide a score whether this object may be a kilonova, a supernova, a microlensing event. And we're working right now also in AGNs and variable stars. So this is an example of a supernova, and you can see that we have 3 different types of scores for the supernova right now. Now, once we have all this information, this is 70% of the stream right now has all this information enriched with the catalogs, VOE events, machine learning scores, features, etc. You can select them in different streams. And this is something we have defined for some science cases that people have asked or we have created, but you can also select yours. So for example, if you're searching a blue transient that is evolving fast near a galaxy, that can be done. And this is an example of the alerts that we received since 2019 from CTF. You can see the heat map of the number of alerts, and then we filter them down to smaller streams of data sets. Now, how can you receive Fink data? There are 2 ways. There's a real-time API, which allows you to trigger robotic follow-up in telescopes. So for example, this could be a Kafka stream, but it can also be, for example, a Slack bot. For example, we have a collaboration with Grandma, and they wanted a Slack bot that basically pinged them every time we have a kilonova candidate. On the other side, we have a more human-friendly way of interfacing with our data, whether it's our science portal, so finkportal.org, or a REST API, which is basically a fancy way of saying that you can query from your terminal or your Jupyter notebook our database and get the data. We want to be this as transparent as possible. All our code is public and all our data is public. So you can reproduce the science that we're presenting right now, just querying our API. Of course, Fink is larger than I am. This is a collaboration. It's our first collaboration meeting. We did it finally this year. We all know that a couple of last years have been complicated, but we're trying to maximize science in all the ranges that we can, from solar system objects to extragalactic objects. We want to touch as many science cases as we can. And you can join us. It's very easy, and we're very happy to hear from other science cases and points of view. So I'm going to center now a little bit more in what we're doing for supernova. And I'm going to touch 3 particular cases. How we can enable supernova follow-up in real time. So for example, partial light curve classification to trigger spectroscopic follow-up. How to get supernova 1A samples without any follow-up. And here I'm going to tell you a little bit about what we have been doing in the dark energy survey. And the third thing is a little bit different. How can we improve training samples for photometric supernova classification? Because we know that training samples right now is one of our weak points in photometric classification and all these machine learning supervised algorithms. So starting with the first one, how can we enable supernova follow-up in real time? So what happens with LSST or CTF will be that we will be receiving these light curves. So brightness evolution over time in the different filters that we get. So CTF is G and R. Of course, LSST will be much more. For me, as a trained eye of looking at eyeballing light curves of supernova for a very long time, I would tell you, yes, this looks absolutely like a supernova. The question is which type? And one of the ways, and the traditional way of doing this, as well as studying the astrophysical process of these explosions, is to get a spectrum. Now, of course, with the volumes of data we're getting from CTF and the volumes of our data we're getting for LSST, we need to filter how many events look like supernova, because there are way too many to trigger follow-up. So one of the things we implemented was we implemented 3 machine learning classifiers, and we asked for 2 of these machine learning classifiers say that this is a potential supernova. That is not an existent transient or catalog object, except if it's in a galaxy. There we are happy. And then we filtered this stream and communicated publicly to the transient name server. So what we have been reporting is around 900 candidates. From these, 600 have been followed spectroscopically. you can see that all of them are supernova except for one. And we have a very high content of type 1a supernova, which was what we were aiming for. And in average, we are reporting them 7 days before peak, which means there is plenty of time to trigger follow-up for this supernova before it fades away. So we're very happy with this, and we're continuing reporting with a high purity, of course, the sample, and we're very happy with it. And this is something that we can think for LSST. We won't be able to trigger every object for follow-up. So how can we do it a little bit better? Now, the other thing I want to tell you a little bit about is, let's forget that we are triggering spectroscopic follow-up live to type the supernova. And let's see how we can actually classify large samples of type 1a supernova, for example, for cosmology, and use them like a very pure sample, probing the diversity of the supernova even better than with a spectroscopic follow-up. So one of the things that we can do is, when you have all these machine learning classifiers, is, well, you wait till the end of the light curve evolution, for example, it has risen, then fallen, faded away. And you can make a probability threshold on selection codes to select a sample, and then use it for astrophysical studies. So in the dark energy survey, we have implemented one of the codes is Supernova, which is a framework I created. And we have been testing type 1a supernova versus non-1a supernova classification. So we have found that the algorithm is quite accurate, with more than 98% accuracy. And together with selection cuts, we can get to contamination levels of 2%. So this is a plot I'm showing you, done by Maria Vincenzi, which I think is it's presential, I think, Maria. And probably she's going to tell you a little bit more about this. And this is a simulation in gray of a cosmology. And you have the contours of the equation of state of dark energy, W, against omega matter. And in red is the supernova classified sample with supernova. And you can see that the good news is that it looks a lot like the simulation, so we are not biasing cosmology. And this is super important because we are using supernova to actually classify supernova for a cosmology analysis in the dark energy survey. I guess a way to see it more visually, and here I'm going to tell you a little bit about the power of doing photometric classification instead of spectroscopic classification. Here, I'm going to show you each of the two black circles is fields of view of the dark energy survey. So C1, C2, C3, it's a 3 fields together. E1, E2, it's a 2 fields together. And in gray, I'm going to show you the number of spectroscopically classified type 1a supernova from the dark energy survey. And in orange, the photometrically classified. So what you can see here is that as time evolves in our survey, and we're talking about 5 years of data, you can see how much more type 1a supernova we have photometrically with the same data compared to spectroscopically. We're talking from a sample of around 400 type 1a supernova spectroscopically classified, we're going to 1,500. So spectroscopic samples of hundreds can become thousands by photometric classification. And this is something that we can use in the power of LSST. Not only is it probing more numbers, but if you see the redshift distribution of these samples, you can see that we're probing a higher redshift, fainter objects, and it's a diversity of type 1a supernova that enables us to study astrophysics even better of the type 1a supernova. So I think one of the biggest limitations we have right now in type 1a supernova cosmology is understanding the environments, things like the mass step, whether the supernova are varying color because of dust. So we can do all these types of studies by having a more diverse sample, because we can select more precisely what we're searching for. And below, I'm pointing a couple of papers that are using this sample that I created with the Dark Energy Survey 5-year data. And I'm pretty sure Maria and Rebecca will be talking about all of these soon, I think tomorrow, I think I'm in the future, so tomorrow may be the other day for you. So this is a very powerful, and I think for LSST, this is something that we need to tackle. We need to do photometrically classified samples, but we need also to understand potential biases that our photometric classifiers can include in the sample. So with, of course, if you have a larger sample, you can do other things like selecting subpopulations and trying to understand subclasses of supernova. And this can also be extended to other types of supernova, like Korkolov supernova, depending on your science case. So the last thing I want to tell you about is a thing that is a little bit different. So why is it different? Well, it's not exactly finding supernova to do the astrophysical studies or the cosmology analysis, but it's more about taking those analyses to the next step. And how can we do it? So usually when you have a machine learning classifier, in particular supervised learning, you have a label pool. This can be real data, or this can be a simulation, for example. You use this label pool to train an algorithm, a machine learning model, which you will then apply to an unlabeled pool, okay? So this will provide you a classification score, and then you will use this to select samples. And this is what I have been showing you till now. However, we know that our label pool, in particular, the data is incomplete. And sometimes it's not the best one or the most representative to actually train the machine learning classifier to make it robust enough for a classification that we trust. And in particular for Rubin, this is a big thing because we will have so many transients and so many variables that we need to think one step ahead. So the idea comes from active learning, and this was introduced in supernova classification by Emily, which I think he was talking today. And the idea is the following. Instead of just applying to an unlabeled pool and selecting the best scores, you select in a smart way the things that are most unsure and decide to follow them up and get a label for them. Once you get a label for them, you inject them back into the training set and you retrain your model, and you keep doing this. The idea is that you select the objects that will help the most to be now included in your training set. And this is a way to optimize as well spectroscopic resources, because we can then pinpoint the ones that will help us the most in the future. So this is a work led by Marco Leoni in the Fink collaboration. The idea was he implemented the active learning loop, and we classified some real supernova from the CTF alert stream. And you can see two methods here. One of them is what we call random sampling. So basically selecting randomly one of the objects in the data set, in the data we have to follow up and then include it into the training net. Or you do it smartly by doing uncertainty sampling, which is the active learning method. And then you can see how that accuracy evolves as we inject one by one new events. And that's what we call the loop. And you can see that the active learning method is getting very high accuracy and very high purity quite fast, faster than random sampling. Of course, this was a little bit of control experiment that we used with data from CTF, and it's the first application of AL to alert stream data. But this is something that we can think to extend in the future. So we can get like a recommendation system where we get, look, if you want to improve training sets, these are all the events that are right now live in CTF or LSST data that will improve training sets in the future. So of course, active learning is super interesting. There is also a talk by Emily today about respect, which is also a recommendation system. And I think this is very interesting to explore for LSST. So I have reached my end of my talk. I hope I have conveyed to you that Fink is online, ready for LSST, but already processing CTF data stream. We have various things that we have implemented for supernova, but not only supernova with photometric classifiers used for cosmology already and trying new things like improving training sets, But we're also working finding kilonova, microlensing event, per-instability supernova, GRB afterglows, solar system objects, etc. And we want that the community still grows. So if you're interested in exploiting CTF or LSST data, we would love to hear from you. I think there are exciting possibilities for core collapse supernova, superluminous supernova, new classification schemes. I would love to hear if you have things that you would like to see in brokers preparing for the future and using data right now from CTF. Thank you very much. If you have any questions, I'm more than happy to answer them.
Thank you, Anais. Questions? You have a quick comment at the end after all the questions. So while you warm up for the question, I will ask you a cheeky question. What's the right number of experts for your active learning models? I know there was some controversy. How many people do you really need to recruit to do the active part effectively?
For this active learning loop?
Mm-hmm.
So this is automatic. We don't need a human looking at the events. It's already automatized. However, we need follow-up facilities to trigger to do this loop. So that will be the people that we would need. But there is no visual inspection in this loop. I know there are some others that do visual inspection. We don't do this here.
Awesome. Thank you. I had misunderstood.
Yeah, no worries. No, there are other active learning algorithms, especially with anomalies, that you try to customize it for humans. Because for me, what is an anomaly may not be the same as for you, but this is not the same. So it's a good question, I think.
Excellent. Any other questions from the audience? Yes.
Hey, thanks for the talk. I was wondering if you could talk more about the early 1A filter and what goes into that, because what we're finding now is that a lot of 1As look quite different at early times.
Yes, excellent question. We're not targeting very rare events, but we are targeting quite classical type 1A supernova here mostly. What it's there, it's very simple, and it's actually, I can point you to the code if you want. We check with cross matches with catalogs that this is not a known object. If it's near a galaxy, it's okay, but if it's not, it's also okay. And then we just simply use the machine learning scores. We ask 2 of these machine learning scores that we have to be above 0.5. So the difference between these machine learning scores is there are 3 algorithms. One of it's early type 1A supernova. So this is Marco's work. So basically it's a sigmoid fit with a random forest classifier that tries to find this rising supernova. Well, the 2 other, the supernova ones, they can classify light curves at any phase. One is trained for type 1A supernova versus non-1A, and the other one is supernova versus non-supernova. So this gives you a little bit of robustness in the sense of discarding some outliers, because it's sometimes hard with alerts that we have other things that look like supernova, like variable stars or AGN evolving in a certain phase. For the very early type 1A supernova, we usually don't get it that early because usually the cadence is about 3 days. So you don't see things like shock breakouts or shock interactions usually in CTF. There are some cases, but counted. So it's very classical type 1A.
One more question.
Thank you, very nice talk. I wanted to ask, do you also classify different types of microlensing light curves? And like
Yes.
And like what are the results like roughly? I mean, I was just curious, like how like what accuracy you get? Like, can you classify like binary microlensing light curves like versus like single lens microlensing light curves?
Excellent question. Completely outside my area of expertise. So I'm going to tell you a little bit of what I know, but if you want, we can chat with the people that are experts on this in Fink. So we have right now LIA as an algorithm for classification of light curves in Fink, where we have identified a series of microlensing events, including some of them that are right now in preparation for publication. When you talk binary microlensing, I'm guessing you're talking about the planetary microlensing with the planet as well, Pike. We are actually sensitive to that. We can see it and we can detect it with this algorithm. It also includes some other cuts. The filter, I can point you to what it is, the filter, because it's all public. I think that's about the extent of my knowledge of microlensing, I must say. But I'm more than happy if you drop me an email to connect you with the people that are doing the filtering for microlensing. In Fink, what we do is a very horizontal collaboration. So if you have a science case that you want to exploit, it's not that you need to report to me or Emily or Julian. Each group is independent and can do their own science. And the idea is to share, but we don't become experts of everything. It's impossible. I would love to, but I need like clones of me.
Thank you so much, Anais. Gautam, do you still have a comment?
Yes, so I just wanted to thank Anais in particular for giving us this talk. LSST is an international collaboration, and this is really exemplifying it because she's giving a talk on a French broker from Australia. And for those of you who complain about the meetings here starting at 8:30 a.m., I'll just point out that Anais did this at 7 in the morning and gave us a really wonderful talk. So thank you so much for the massive time.
Indeed,
Thank
massive
you.
thank you, Anais.